Good evening. Welcome back to the module Communication Theory, Learning Outcome 3, Topic 11. In this topic, we are going to study about characterization of bandpass thermal noise and performance of linear modulation systems in noise. In the previous session, we studied about the what do you mean by thermal noise and the effect of thermal noise in RC network. And then we studied about the white noise and filtered white noise. After that, we studied about the bandpass noise. So the thermal noise usually it is occurring in the thermal resistor, and we measure the what is the output power of the thermal resistor. It is equal to kT by 2. So from this we can note on that the output power of the thermal resistor does not depend on the resistance R. And coming to the thermal noise in the RC network, and we observe the output power of the RC network, which is equal to kT by C, where C is the capacitance of the RC network. Then we studied about the white noise. White noise, it has the power spectral density Gn of f equal to nr by 2, and where n naught equal to the product of k into T, where k is the Boltzmann constant, T is the absolute temperature. And then when the white noise is passing through the filter, then the filtered white noise, it has the output power that is equal to n naught G into B, where G is the gain of the filter and B is the bandwidth of the filter. Then coming to bandpass noise, bandpass noise is usually occurring in the analog communication system. When the white noise is passing through the bandpass filter, then the output of the bandpass noise we can call it as the bandpass noise. Okay, and then today's session we are going to discuss about the characterization of the bandpass thermal noise. So before going to discuss about the thermal noise, we need to know the another important parameter which is called signal to noise ratio. So we are going to discuss some important points about the signal to noise ratio. Let us see the diagram for the model of the received signal with the additive noise. Okay, there is a input signal, received signal, which is generated by XR of T, and there is a additive noise whose power spectrum is Gn of f equal to n naught by 2. So the received signal XR of T is added with the additive noise. Then the combined signal is given into the linear receiver. So the linear receiver, it may be a low pass filter. Then after filtering by the linear receiver, we are getting the output signal which is denoted by Yd of t at the destination. So the Yd of t is the received signal at the destination, which is the combination of xd of t and the nd of t, where xd of t is the signal power at the destination, nd of t is the noise component at the destination. So So the received signal is the summation of the transmit signal x of t and the noisy signal n of t. So from the received signal yd of t, we can find out what is the total output power. So in order to find out the total output power, we have to find out what is the mean square value of the output signal yd of t. So which is yd squared of t. Yd squared of t is the mean square value of the received signal at the destination. So which is because of the received signal at the destination consists of the decided signal and the noisy signal. So we can apply the mathematical formula a plus b whole squared. So it has the three terms a squared plus 2ab plus b squared. So that is the signal term and the product of the signal and the noise term and the square of the noise term. And here we need to apply we have to consider the two reasonable assumptions for additive noise. The first assumption is that the noise comes from an ergodic sources with a mean zero and a power spectral density Gn of f, which is equal to n naught by 2. And another assumption about the additive noise is that the noise is physically independent of the signal, and hence it is uncorrelated with the signal term. So with this assumption, we can take the second term, that is the product of cross product of the XD of t and the NT of t equal to 0, because both are the signal term and the noise terms are uncorrelated to each other, so that the cross product of XD of t and the ND of t equal to 0. So therefore, we can get the statistical average of the received signal at destination, YD squared of t. Another notation for the statistical average of the received signal as a destination is that YD squared bar, which is the mean square value of the received signal at destination, which is equal to XD squared bar plus ND squared bar, means the signal power and the noise power, okay, plus noise power. So we can say this is the superposition of the signal term and the noise term at the destination. And we can represent the received signal power at the destination by the another notation, that is SD. And the noise term, noise power at the destination is denoted by ND. So ND is the noise power at the destination, SD is the signal power at the destination. So which is measured by calculating the mean square value of the signal term and noise term. So therefore, we can write the mean square value of the received signal YD square bar equal to simply SD plus ND. So by using these two terms, we can find out what is the signal to noise ratio at the receiver destination. And for the assumption of the given receiver gain is GR and noise bandwidth BN, then the destination noise power will be calculated as ND. ND means the noise power at the destination, which is equal to GR into N0 into BN, where GR is the gain of the receiver and N0 is the noise density is a product of K into T, and BN is the bandwidth of the filter. And we can assume that the noise is the noise following Gaussian distribution. Then we can call such kind of noise is called additive weight Gaussian noise. Okay, where N not equal to K into Tn, where is the noise density, and where K is the Boltzmann constant, and Tn is the noise temperature. So this plot diagram shows the complete analog baseband transmission system in the presence of noise. So we can see here the input signal is exactly given into the transmitter. The power of the input signal is measured by measured as a SX, where SX indicate the transmit signal power. Then the transmitter gain is denoted by GT. Then the output of the transmitter power is measured as ST. So which means that ST is the transmit power, SX is the signal power. So after passing through the transmitter section, we are measuring the transmit signal power, that is ST. And then the signal will be propagated into the medium channel. So the channel having some losses, distortion losses, and that is denoted by capital L. So capital L is the channel transmission loss. And then the output of the channel is the received signal, that is denoted by XR of T. And then from this received signal XR of T, we can find out what is the received signal power, that is denoted by SR. So SR is the signal power of the receiver. Then the received signal from the channel is added with the white noise. It has the power spectrum GN of F. GN of equal to N0 by 2. Then the addition of these two, the received signal and the noise is passing through the receiver section. The receiver section is consist of the low pass filter and the another portion which is compressed by the receiver gain GR. Okay, like in the transmitter side, all the transmitter portion contribute to the transmit gain GT. So the GT is the transmitter gain. It is coming from the transmit section. Okay, the modulator and and so on. Similarly, at the receiver side, that low pass filter and band pass filter, all this combination we are considering as a the receiver gain. Okay, at the transmitter gain particularly coming from the antenna dimension, antenna aperture. Okay, the antenna materials. So we are calculating as a transmitter gain GT. Okay, so so the signal is passing through the receiver section, which has the receiver gain GR. So after that, it will pass through the low pass filter. Then finally, we are getting the receiver signal at the destination. That is the output of the low pass filter, which is equal to the addition of the signal term XD of t and the noise term ND of t. Or we can write simply as a SD plus ND in terms of power of the receiver signal. So there are three important power measurement in the analog communication system. That is ST. SD means and the transmit signal power. SR is the receive signal power, and SD is the destination signal power. Okay. So the transmit signal power is GT into x squared bar, where x squared bar is the mean square value of the transmit data. GT is the transmitter gain, so the x squared bar is the mean square value of the transmit signal. So it will give the transmit signal power, that is Sx. So the transmit power St equal to Gt into Sx, and the received signal power Sr equal to XR squared bar. Okay, so which is equal to St by R because of it experiencing the channel transmission loss, so that the received signal power SR equal to St by L, where L is the channel transmission loss, and SD is the destination signal power. Okay, so the difference between SR and SD, the SR power is measured after the signal coming out from the bandpass filter, whereas the SD power is measured after the signal coming from the low pass filter, because the receiver it has the both the bandpass filter and the low pass filter. So therefore, the SD equal to XD squared bar, so which is equal to GR into SR. Okay. So therefore, we can find out what is the signal to noise ratio. So the signal to noise ratio of the destination equal to this ratio of the signal power to the noise power at the destination. So it is denoted by and the ratio of S by N of T. Okay, which is equal to the signal power SD equal to GR into SR. We have to substitute. Whereas noise power ND equal to the product of GR N naught into W. So where W is the bandwidth of the filter. Okay, BN equal to W. So the GR will be cancelled. Finally, we are getting the signal to noise ratio at the destination equal to SR by N naught into W. So the main expression for the signal to noise ratio calculation at the communication receiver. So the signal power SR and noise power depend on the bandwidth of the filter. Okay, so that we are getting N naught into W. And we can replace the received signal power SR by ST by L. Okay, so then we can get the another expression for the signal to noise ratio at the destination. So which is equal to SD by L into N naught into W. Okay. And as we know that the N naught is the noise density, it is the product of the K into Tn. And for convenient, we can add both numerator denominator by the standard temperature T naught. Okay, so we can rewrite the N naught equal to 4 into 10 power minus 21 into Tn by T naught. So the unit for the noise density is watts per hertz. Means the we are measuring the noise power per hertz, right? So the typical value for the noise temperature it varies from point 0.2 T naught to 10 T naught, and we can measure the signal to noise ratio in terms of decibel. Okay, so we know the final expression for the signal to noise ratio, which is SR by KTN into W, where KTN equal to N naught. So we are replacing that N naught by K into Tn. So therefore, we are getting that SR by KTN into W. Because of we need the value in decibel, we have to take the logarithm. So 10 log of SR by K Tn by W. By applying that log rules, log m by n rules, we are getting the signal power in dBm plus 174 minus 10 log of Tnw by T naught. So this is the expression for the signal to noise ratio in terms of decibel. And here that 127, 174 is coming by that k into t naught, because here we are multiplying both numerator and denominator by t naught, so that we can separate the k into t naught, it will be equal to 174. So the remaining term is the tn by t naught into w. So that is the last term, tn by t naught into w, right? So for this expression, similar to noise ratio expression, we can see one example. Okay, the consider a cable system. It having the loss, transmission loss L equal to 140 dB, which is equal to 10 power 14, and the noise temperature Tn equal to 5 into T naught. If you want a high fidelity audio transmission with bandwidth W equal to 20 kilohertz, and the destination signal to noise ratio greater than or equal to 60 dB, then what is the signal power? What is the transmit signal power? That is the question. So we can use this above formula, the signal to noise ratio in dB. So we have to substitute that Tn equal to 5 into T naught. Okay, so by substituting Tn equal to 5 into T naught, so T naught will be cancelled. So in that bracket time, we are getting 5 into W. So where W is the bandwidth which is given 20 into 20 kilohertz. So therefore, we are writing here 5 into 20 into 10 power minus 3. So and the signal to noise ratio destination also given, that is 60 dB. So by substituting all these values, so we are getting that what is the received signal power, right? What is the received signal power? That is SR in dBm, which is equal to 4 into 10 power minus 17 milliwatts. And if you know the received signal power, then we can find out what is the transmit power. Because we know the relation between signal power, transmit power and received power. So therefore, we are getting the transmit power ST equal to L into SR. So we are getting the transmit power equal to 4 into 10 power 17 milliwatts, or we can write it is a 40,000 watts is required. Okay. Okay, now coming to the another topic, pulse measurement in the noise environment. Okay, you can see the system model for the pulse measurement in the presence of additive weight Gaussian noise. So the block diagram shows the input signal. This is a pulse P of T, and the noise is added. Okay, the spectrum of the noise is N naught by 2, so pulse spectrum of the noise. Then the added signal is given into the low pass filter. It has the bandwidth Bn. Okay, then the output of the low pass filter is Y of t equal to P of t plus N of t. Here the input signal is the pulse. We are sending that pulse. The pulse may be a rectangular pulse or a trapezoidal pulse. But in this discussion, we are considering the transmit pulse as a trapezoidal pulse. So because of the combined signal pass through the low pass filter, the excess noise component will be removed. Okay. So then the output signal at the time instant ta, we can write y of ta equal to a plus n of ta. Where ta is the time instant at which the signal is measured at the destination. And so the n of ta equal to epsilon a. So the epsilon a is the amplitude error. Okay, the epsilon a indicate the amplitude error is a act as a noise to follow the Gaussian distribution. So we can find out what is the error variance for the amplitude error, so which is denoted by sigma a squared. So the sigma a squared, where the subscript a denote the error coming from the amplitude, so that we are using. So sigma a squared equal to n squared bar, which is equal to n naught into bn. And now consider the power of the is signal a squared equal to ep by tau, and the bandwidth is bn. Then the noise variance sigma a squared equal to n naught by n naught into bn. So, but bn equal to 1 by 2 tau, we have to substitute. So, n naught by 2 tau. And also from this a squared equal to eb by tau expression, we know what is the tau. So, tau equal to eb by a squared. So, finally, we are getting that the noise variance of the amplitude error sigma a squared equal to n naught a squared divided by 2 into ep. So here you can see that the transmit pulse, it is a trapezoidal pulse, and it has the amplitude a, and the duration of the pulse is tau, and the energy of the pulse is denoted by ep equal to a squared into tau. Okay. And from this pulse, we can see that from this graph, we can see that there is a original trapezoidal pulse. That is the ideal shape of the trapezoidal. But after experiencing noise, the trapezoidal shape will be distorted. So the distorted pulse is the received pulse, and this is the original trapezoidal pulse. There are two waveforms are showing in this graph. Then we are measuring the sample at a time instant Ta. So at a time instant Ta, the pulse has the magnitude A plus n of Ta. So A is the amplitude of this transmit signal. N of Ta is the noise power at the time instant Ta. Okay. And here the TR indicate the rise time. Okay, rise time where the detector going to detect the received pulses. So the rise time of the pulse TR equal to 1 by 2 into Bn. And like amplitude error, due to that time disturbance, okay, some error will be occurring, that is called noise perturbation, causes by the time positioning error. Okay, that is denoted by epsilon t, like epsilon r. So epsilon r is the amplitude error, whereas epsilon t is the time positioning error. So due to that the noise perturbation, so not to understand that time positioning error, you can see the only portion of the trapezoidal wave. Okay, the usually at the receiver side, the receiver going to detect the pulses whenever the amplitude of the pulse is above a by 2. The received signal amplitude is above a by 2. Then the receiver going to take the decision of the received pulses. But due to the noise is added with the transmit signal. Okay, the original position of the pulse, for example, we can see here. So this is the actual the a by 2 of the trapezoid pulse. Due to the noise is added, see the position of this pulse is shifted from this position to another position. Okay, so the time positioning error is occurring, that is denoted by epsilon r. So then you can see from this graph that epsilon t and n of t, it looks like a right angle triangle, and we can equate this epsilon t and n of t ratio to the amplitude a to the rising time tr. So therefore here we are writing that the ratio of epsilon by n of t equal to tr by a. From this we can get the time positioning error epsilon r, sorry, epsilon t equal to TR by A into N of dB. So by using this time positioning error, we can find out what is the noise variance due to that time perturbation. That is sigma t squared. So sigma t squared equal to the ratio of TR by A whole squared into n squared bar. So the n squared bar is the noise power, that is the product of N naught into Bn. Now substitute the rising time TR equal to 1 by 2 Bn, and the amplitude square A squared equal to EB by tau. So finally we are getting that noise variance due to the time perturbation, sigma t squared equal to N naught T by 4 Bn into EP. Okay. So this is the concept of how the noise is affecting the transmit pulse at the receiver. Okay. Next, coming to the matched filter. This is another type of receiver which is used to detect the transient pulse at the receiver. So the matched filter is the optimum filter which is used to detect the pulses at the receiver in the presence of additive noise. So the received pulse is denoted by XR of t. XR of t equal to AP into P of t minus T naught, where P of t is the transmit pulse is which is received with some delay T naught, and it has the amplitude AP. So here the block diagram shows the matched filter. Okay, in the okay, in the presence of the additive white Gaussian noise. Okay, so the received signal is XR of t. Then it is equal to AP into P of t minus T naught. So that is the transmit pulse received with some time delay T naught, and that received signal XR of t is added with the white Gaussian noise with the power spectrum Gn of f, and it passes through the matched filter. It has the response H of f. Then finally we are getting the output signal, which is Y of t. Okay, so the second the waveform shows the filtered output, the Y of t. Okay, the y-axis is the amplitude of the filtered output signal. X-axis is the time duration, and we are measuring the sample at a time instant t naught plus td. Okay, it has the magnitude a plus n. Okay, at a time instant t naught plus td, we are measuring the sample of the filtered output. It has the magnitude a plus n. Then for this signal, we can find out what is the Fourier transform of the received signal. So the received signal is XR of t, so which is equal to AP into P of t minus t naught. So now we need to find out what is the Fourier transform of the received pulse. So we are getting XR of f equal to AP integral minus t by 2 to plus t by 2 P of t minus t naught e power minus j omega t is a Fourier transform formula. We are substituting that received signal XR of t. Since there is a delay in the pulse, we have to use the another variable n. So n equal to t minus t naught. So by replacing n equal to t minus t naught, we can write XR of f equal to AP integration P of n e power minus j omega. The t will be replaced by n plus t naught, because n equal to t minus t naught, so that we can write t equal to n plus t naught. Okay, so it will be equal to AP PFF into e power minus j omega t naught, right? Where P of f equal to minus integration minus t by 2 to t by 2 P of n e power minus j omega n is a Fourier transform of the transmit pulse P of n. So then from that received signal, we can find out what is the total received pulse energy, which is equal to EP. So now to find out the total received pulse energy, we can integrate the squared magnitude of the XR of f. Okay, so that we are getting AP squared integration minus infinity to plus infinity, the squared magnitude of the PFF in okay. Here that e power minus j omega t, the absolute value of e power minus j omega t equal to 1. So the receiving filter having the pulse energy, okay, which is equal to the output pulse energy with amplitude of A. Okay, so the peak pulse amplitude of the output of the matched filter is denoted by capital A, is the inverse Fourier transform of H of f into XR of f, because we are matching the received signal with the frequency response of the filter, matched filter H of f. Okay, we can substitute the XR of f, and we can simplify because of the inverse Fourier transform. Here we are using the e power j omega t naught plus t naught plus td, because it's a time instant where we are measuring the sample at the receiver, so that we are substituting t naught t equal to t naught plus td, and then after simplifying we are getting AP integration h of f p of f e power j omega td into df. So that is the peak pulse amplitude of the matched filter. Then we can find out the noise variance of the transmit pulse at the destination. So which is sigma squared. Okay, it's the integration of frequency response of the matched filter and the noise power spectrum GN of it. Then we have to substitute both signal power, means peak pulse amplitude and noise variance. So we are getting what is the signal to noise ratio for the transmit pulse in the presence of additive noise. That is denoted by ratio of A by sigma whole squared. So here the matched filter is a optimum filter. It has the frequency response is denoted by H optimum of f equal to k into p conjugate of f e power minus j omega td by gn of f. Okay, so that is the frequency response of the matched filter, or we can call it optimum filter. And from that frequency response, we can find out what is the impulse response by taking inverse Fourier transform of the frequency response H optimum of f. Okay, so we are getting by substituting that value. Since we know that g n of f equal to n naught by 2, we have to substitute. So we are getting 2k by n naught, and here already in that frequency response there is a e power minus j omega td is there. We have to use as it is. It is this second exponential coming from the inverse Fourier transform, and we have to combine the power in the exponential term. So we are writing like e power minus j omega td minus t. So it will be equal to p of td minus t. So, transient pulse with the delay td. Okay, so next coming to the topic characteristics of bandpass noise. So already in previous session we studied about the bandpass noise. When the white noise is passing through the bandpass filter, then the bandpass noise is occurring in the communication system, especially at the receiver. Okay, we can represent the bandpass noise in various form, like quadrature form or envelope and phase form. So now we see the bandpass noise in quadrature form. Okay, so now consider the bandpass noise n of t as a sample function of the AWGN process, and then its mean and the variance we can calculate, that is denoted by n bar. So it will be 0. Then the variance is n squared bar. That is the mean square value. Mean square value also you can call it the variance sigma squared equal to nr, means the received the noise power at the receiver. Nr indicate the noise power at the receiver or variance. So the noise in band pass form. Okay, we can represent this is the expression for the quadrature form of the bandpass noise n of t, and the first term is the in phase component, second term is the quadrature component. So that is ni of t cos omega ct minus nq of t sin omega ct. And both in phase and quadrature components are jointly stationary and Gaussian. And it has the several properties. The bandpass noise has the several properties in quadrature form. So that the mean value of the in phase and quadrature component equal to 0, and the cross product of the in phase and quadrature component equal to 0, and then mean square value of the in phase and quadrature component equal to n squared bar, which is equal to nr, means the noise power and the received noise power. And we can represent the bandpass noise in another form, such as envelope and phase of the bandpass noise, which is denoted by n of t equal to an of t is the envelope of the bandpass noise, into cos of omega ct plus pi n of t, where pi n of t is the phase of the bandpass noise. So this diagram shows the phasor diagram of the bandpass noise. From this diagram, we can find out what is the magnitude of the bandpass noise and what is the phase of the bandpass noise. Okay. Okay, so from this phasor diagram, we can find out what is the an squared. So the an is the diagonal element, and nq is the opposite element, and ni is the adjacent element. Okay. So by using that right angle triangle formula, we can find out. So the diagonal value equal to an squared equal to ni squared plus nq squared. And we can find out what is the pi. So pi is the tan inverse of opposite side by adjacent side. So nq by ni. So this is the another form of the bandpass noise where we are measuring the magnitude and the phase of the bandpass noise. And since the bandpass noise is the random, we can find out what is the probability density function of the envelope of the bandpass noise, that is an, which follows the Rayleigh's distribution, with the mean value an bar equal to square root of pi nr by 2, and the variance an squared bar equal to 2 into nr. So this expression shows the Rayleigh PDF function for the envelope of the bandpass noise an, okay, which is equal to Pan of an equal to an by nr e power minus an square by 2 nr into u of an. So using this parameter, we can see one example for the bandpass noise, envelope of the bandpass noise. Okay. Suppose bandpass noise with nr equal to 1 microwatts means the received noise power nr equal to 1 microwatts is applied to a 1 ohm resistor. Calculate the mean and RMS value of the envelope voltage. So we can directly use the formula for mean and RMS value. So the mean equal to an bar. Okay, so nr is already given, that is 1 microwatt, that is equal to 10 power minus 6. So after simplifying, the mean value equal to 1.25 microwatts we are getting. And for RMS value is sigma an equal to square root of an squared bar minus an bar. So here the an squared bar is the mean square value of the envelope, and an bar is the mean value of the envelope. So by substituting, simplifying, we are getting RMS value of the envelope voltage equal to 0.866 microwatts. And we can see the correlation function of the bandpass noise. So for that, we can write the low pass equivalent of the bandpass noise, that is n LP of t equal to 1 by 2 n of t plus j n cap of t into e power minus j omega t. It is looking like a Fourier transform of the bandpass noise. And here uh, n cap of t is the Hilbert transform of the bandpass noise n of t. Okay, and so we can write the this is the low pass equivalent of the band pass noise is denoted by n lp of t, where subscript lp indicates the low pass. And in terms of quadrature form, we can write the band pass noise. Okay, so n lp of t equal to 1 by 2 into ni of t plus j nq of t in phase and quadrature component, which means we are representing low pass equivalent of the band pass noise in two forms. Okay, one is in complex number and another one is the in phase and quadrature form. Then we can equate both equation. Okay, means that 1 by 2 is a complex form, 1 by 2 ni of t plus j nq of t is a quadrature form, which is equal to the complex form 1 by 2 n of t plus j n cup of t e power j minus j omega t equal to cos theta minus j sin theta. Then we have to separate the real and the imaginary part. Okay, so that okay, we are separating real and imaginary part of the low pass equivalent of the band pass noise. So the real part gives the in phase component, imaginary part gives the quadrature component. So the ni of t equal to n of t cos omega ct plus n cup of t sin omega ct. So the real part of the low pass equivalent, which is equal to in phase component. The imaginary part of the low pass equivalent gives the quadrature component nq of t. Okay. So which shows the relationship between the quadrature components and the n of t. Okay. So then next we are going to discuss about the last topic, linear modulation in the presence of additive white Gaussian noise. Okay. Okay, so you can see the model of the receiver for the continuous wave modulation in the presence of noise. Okay, the input signal is denoted by Xc of t. Xc of t is the carrier modulated signal whose power is calculated as SR. So SR is the received signal power, and where the noise is added, it has the power spectrum G of f equal to N naught by 2. Then the combined signal will be given to the bandpass filter. Okay. So the main thing in the linear modulation based receiver, it is at the receiver side, it consists of the bandpass filter and detector and then low pass filter. So for bandpass filter, the response is HR of f, and for low pass filter, it has the frequency response HD of f. Okay. Now we can assume that the combined signal and the noise is given to the bandpass filter. Then the output of the bandpass filter is V of t, which is equal to Xc of t plus N of t. So where N of t is the bandpass noise because it is the output of the bandpass filter. Where we can measure the signal to noise ratio, that is S by N of R. Okay, means the signal to noise ratio of the receiver. Then the V of t is given to the detector. Okay, the detector, it may be envelope detector or synchronous detector, where the signal will be detected. Then it will be denoted by Y of t. Then this Y of t output of the detector is given to the low pass filter. Okay, where the unwanted frequency component will be removed. Finally, the output of the low pass filter gives the received signal Yd of t. From that, we can find out the final signal to noise ratio or the destination, that is denoted by S by N of t. So S by N of t is the signal to noise ratio or the destination. S by N of R is the signal to noise ratio or the receiver. Okay. So the signal to noise ratio. So signal to noise ratio at the receiver equal to the ratio of SR by NR. Okay, it is equal to SR by NR is the noise power at the receiver, which is equal to N naught into BT, because it is a band pass noise, so that the noise density is multiplied with the bandwidth of the band pass filter BT. Okay. So we can represent the bandpass noise in quadrature form, so that it has the in phase component and the quadrature component. Yeah, that is the n of t. It has the in phase and the quadrature component. Then we can find out the mean square value for the bandpass noise. So we know the properties of the bandpass noise, so that the ni squared ni mean square value of the in phase and the quadrature component will be equal to nr. So nr equal to n naught into bt. Okay. So that is the received noise power. nr equal to received noise power equal to n naught into bt. So we can use the demodulation process. There are two type of detector we are using: synchronous detector and the envelope detector. For synchronous detector, y of t equal to vi of t, which means that synchronous detector it only extract the in phase component. Okay, so now we are going to discuss about the synchronous detector. So the synchronous detector, it is simply extract the in phase component of the P of t, where V of t is the output of the bandpass filter. Okay. If you consider the modulation is double sideband, then the signal Xc of t equal to AC X of t cos omega Ct. It's the equation for the double sideband modulated signal. Okay, where AC is the amplitude, X of t is the transmit data, cos omega ct is the carrier signal. Then the pre-detection signal V of t is the output of the bandpass filter. Because of okay, it has the in phase and the quadrature component. Okay, so AC X of t plus NI of t cos omega ct minus NQ of t sin omega ct. Okay, here we can observe that the synchronous detector output will extract only the in phase component. They extract only in phase component of the transmit signal, so that the pre-detection signal it consists of the in phase component of the transmit signal, that is AC X of t, and the in phase of the noise component is added NI of t. Okay. Because of the noise component, there is a quadrature part is present. Then the output of the synchronous detector, the output of the synchronous detector is Yd of t, which is equal to Vi of t. Okay, so it extract only the in phase component, so it will be equal to AC X of t plus Na of t. So you can see here the pre-detection signal is the output of the bandpass filter, which has the in phase and the quadrature component. Okay, but even though the signal term it is coming only the in phase component, due to the noise, it is a in phase and quadrature. But synchronous detector, it remove the quadrature term and it allow only the in phase component. So therefore, we are getting that AC X of t plus Na of t. From that signal Yd of t, we can find out the mean square value. That is Yd squared bar equal to. So because the signal term is amplitude AC, okay, so AC squared X of t, the power is Sx. The noise term whose mean square value is Ni squared bar. So we can write this term is Sd, the second term is Nd. And we can find out what the SR for the double sideband modulation. SR equal to Xc squared bar, which is equal to AC squared Sx by 2. Which give the AC squared SS equal to 2SR. Okay. So we can here, you can see here the signal term is AC squared XS. So we can replace this AC squared SX by 2 into SR. So the 2 into SR equal to SD. Okay. And so here we are considering the pre-detection filter, and it has the bandwidth BT equal to 2W. And so this is the output noise power spectrum formula, which is equal to n naught into pi of f by 2w, where pi of f by 2w is the rectangular function. So post reduction SNR. So post reduction SNR means after passing through the low pass filter. we are measuring the SNR, that is called post reduction SNR. It is the ratio of SD by ND. So we already got the expression for SD. So SD equal to 2 into SR. Okay, we have to substitute here 2 into SR, and a noise power equal to ND means noise power destination. It is equal to product of N naught into BT. Okay, and we can write this term as 2 into S by the ratio of S by N of R. So which is denoted by gamma. Gamma is the signal to noise ratio at the destination. Because we are using that double sideband modulation, we can write the bandwidth BT equal to 2W. So replace the BT equal to 2W. So 2 will be cancelled. Then the signal to noise ratio at destination equal to the ratio of SR by NRW for double sideband modulation. Now consider the single sideband modulation. For single sideband modulation, the received signal is YD of t, which is equal to 1 by 2 AC X of t plus NI of t. Okay, only the in-phase component is coming. But for double sideband, the bandwidth is 2W. For single sideband, the bandwidth BT equal to W only. Okay, so we can find out the mean square value for the received signal using single sideband, which is equal to AC squared by 4 into Sx plus Ni squared bar, which is equal to SD plus ND. Signal term, signal power at destination and noise power at the destination. And here the SD equal to this term AC squared Sx by 4, and it will be equal to signal power at the receiver. This is the power spectral density for the single sideband, okay, which has the N0 by 2 into rectangular function. And the output noise power for single sideband, because of single sideband bandwidth B equal to W. So ND equal to N0 into W, which is equal to NR. So therefore, signal to noise ratio at destination equal to signal to noise ratio at the receiver. Both are equal. Means the signal to noise ratio at the bandpass filter is equal to signal to noise ratio at the low pass filter for the single sideband. Then we consider the AA modulated signal, okay, which is equal to Xc of t equal to AC of 1 plus X of t cos of omega ct. So this is the mathematical expression for AM modulation. Then the received signal is YD of t equal to AC 1 plus X of t plus Ni of t. Noise is added, and here the signal power is calculated, that is SD equal to AC squared into Sx. Because here the synchronous detector block the DC component, so that one will be removed. So we are getting the signal power at destination equal to AC squared Sx, and the noise power ND equal to N0 into W. But for unmodulated carrier power, the received signal power equal to AC squared plus 1 plus Sx by 2. Okay, here we can consider that DC component, so that we are getting AC squared into 1 plus Sx by 2, where Sx is the transmit data power. So from this we can see that what is AC squared. So AC squared equal to 2 into SR by 1 plus Sx. So we can replace here the SD in the AC squared in the SD term. So therefore SD equal to 2 into Sx SR divided by 1 plus Sx, right? Because SD equal to AC squared into Sx. Here the AC squared is replaced by this term. AC squared equal to 2 into SR divided by 1 plus Sx. So that we are getting the signal power destination equal to this expression. So for AA modulation, so signal to noise ratio at the destination equal to 2 into Sx XR divided by 1 plus Sx into NR. And we can separate this term, that 2 into Sx divided by 1 plus Sx into S by N of R. Okay. So finally, we are getting that 2 into Sx by 1 plus Sx into gamma for AA modulation. Actually, this 2 not coming, okay, because the 2 into S by N of R equal to gamma that we got for the AM double sideband modulation. 2 into S by N of R equal to gamma. Okay, that is a mistake. So that here we only Sx by 1 plus Sx into gamma is coming for AM modulation. And if you consider if Sx, that is the power of the transmit data, Sx less than or equal to 1, then the signal to noise ratio of the destination will be minimized to gamma by 2. Because if you substitute Sx equal to 1, so 1 by 1 plus 1 equal to 1 by 2. So gamma by 2 is coming for AM modulation. And for full load tone modulation, Sx equal to 1 by 2. So by substituting Sx equal to 1 by 2, then we are getting that signal to noise ratio equal to less than or equal to gamma by 3. So which means that for that case, the signal to noise ratio for AM modulation is 5 dB below the double sideband modulation. Okay, thank you. So today's session we studied about the some important points about the signal to noise ratio calculation. And then we studied about the pulse measurement in the presence of additive white Gaussian noise. After that, we studied about the characterization of the bandpass noise. Then we studied about the linear modulation in the presence of additive white Gaussian noise. Thank you.